All right, we are live. Hi everyone, I'm really excited for this session, and I know Daniel very well. We met at Social Algorithms workshop last year, and both of our teams did amazing projects at that time. And with more AI AEC tech workshops and sessions, we frequently met, and he's an amazing guy to work with. Yesterday, we spent the whole day to develop some custom environment in Unity, and we are very excited to share it with you. He's currently a master's in computer science student at Georgia Tech. He's also co-founder of Ola Research, and he's doing amazing work. And we discussed like the latest technology in or research paper in machine learning, and keep ourselves updated. So thanks, Daniel, for your time to do this, and I can't wait to share stuff.
Yeah, thank you, Mary, for having me.
Cool. So the way we are planning the structure of today's session is we'll give you very high level overview about reinforcement learning. We'll discuss one or two papers on how reinforcement learning has been deployed in architecture, then go through a basic procedure how to set up reinforcement learning environment and in Unity, and lastly we'll share our experiment we did yesterday. So as you all know, like the three major types of learning in AI is supervised, unsupervised, and reinforcement. Where supervised has classification and regression problems can be solved through that approach. Unsupervised has clustering, anomaly detection, association, autoencoders falls in that category, and reinforcement is more on the behavioral and policy training. And you might have seen like AlphaGo, quite popular uh, game developed based on reinforcement learning, and it it shared move 37, which were quite creative. So basically, like the key components which involves in reinforcement learning train algorithm is like identifying what is the agent, what is the action space for that agent, what are the features that the agent needs to observe in the observation space, how do you define the environment, and then the reward function for it. So the way it works is for each time step, you look at the current observation space, you based on like the training, it predicts what next action you should take to maximize the reward. And that's how there are uh, like the policy is being developed that maximize cumulative rewards in long run.
And one thing to add about like the difference between reinforcement learning and all the other types of learning, like supervised and unsupervised, is that in where the other two, you're pulling data from other sources. In reinforcement learning, or like the kind of like the interesting part about it is that it's generating its own data. So you can start from scratch in an environment with an agent, and the agent would generate its own data through interactions with the environment. And through those interactions, dependent on how you would structure the reward. So meaning how you want the agent to modify its behavior to maximize some sort of reward, the agent will learn a policy. And that policy, essentially, you can either have it be optimized as possible, or you can have it be a little bit more exploratory and allow the agent to learn a little bit more and explore the wider space of actions.
Yeah, that's a really good point. And many times I see reinforcement learning as like our smart assistant, because based on the training objective function, you can like give them rewards and train them really well in a task. So there's a teaser video on my channel where Pedro was showing like human machine architecture planning, where human does some step and then other rooms get self-organized to make it better in terms of daylighting and structural performance. So those agents are can be trained to help a human being to make better design rather than overcoming everything. So, and also like in AlphaGo, earlier people were like skeptical that it's gonna no human will now be able to beat AlphaGo, but now people are learning more behavioral techniques and getting better by working with machine. So instead of having a pessimistic, I see like more better learning practices using those kind of agents. Yeah. So like there are a lot of different algorithms based on discrete space, action space or continuous action space, model free or model based learning, uh, deep Q learning techniques, policy optimization. So for our discussion purposes, we are focused more on PPO. And yeah, so Daniel, maybe let's discuss few architectural applications.
Sure. I was gonna say like there's like kind of like a huge if you go back to the slide, Mayor,
Yeah.
just to discuss like a little bit of the type of RL. So the model free RL versus model based RL. So the interesting part about the model free RL is that you don't have to essentially uh, recreate the environment in some way. You can kind of just drop an agent in an environment, and through that interaction with the environment, it's gonna learn. Which that's kind of what makes it. Makes it really popular and really flexible. And for example, one of the most famous RL papers was the paper where DeepMind taught agents using DQN, which is deep Q networks, to play a whole bunch of Atari games. The interesting part about it and why it was model free, it was that they pretty much use the same algorithm for all the types of Atari games that exist. And they didn't change many of the, let's say, the hyperparameters. But after the model was able to learn, it was able to perform pretty well, regardless of the environment. So that's kind of like the flexibility that you can afford with using a model-free reinforcement learning agent.
Like many people are also say it's reinforcement learning could be a direction towards generic uh, uh, like what AGI.
Yeah, it's possible, right? Because I guess in this sense, you kind of started from scratch and you're letting just the agent make its own decisions and produce its own data. And then essentially what that leads to is that the agent is going to try to pick the actions that would benefit him the most, which is interesting. Like there has been some work where they're trying to frame more and more problems. Like as of recently, like out of I think it was Berkeley or Stanford, that they allowed uh kind of like a hand to be trained, right? And the hand master its ability to like pick things, rotate them, and all this type of stuff, which that's kind of fascinating, right? Like it just learned to do that. And it's something that you would think it would be kind of hard, but the things that it was able to do with such dexterity just kind of shows like the promise of this type of stuff.
I see. Cool. Do you wanna share screen?
Uh, yeah, so let me so where's the paper? So I'm gonna run through a paper that shows an example of how you can structure a simple RL agent in an architectural environment. Um, this was a paper coming out of CAADRIA 2021 by let me share my screen real quick. By Dasung Wang and Roland Snooks. So this paper is called Intuitive Behavior and the Operation of Reinforcement Learning in Generative Design Processes. Um, so I thought that this was a pretty interesting paper in the sense that they're kind of using the sort of one of like the interesting properties of RL to generate like what they call it kind of like some sort of surface that acts kind of like a pavilion. Um, and the interesting part about this is that you're pretty much just given a few constraints to generate the surface, and they essentially create their own environment and define the way that the environment should respond to those constraints. So one of the key parts, like we said before about a reinforcement learning problem, is that you need to define like what's the agent, what is the environment, what are the actions that the agent can take in that environment, what are the observations or the states, meaning what does the environment provide to the agent where the agent can then take actions, and then the rewards, which just means essentially what does it get, what does the agent get by taking the actions at each time step. Or you can also set the rewards instead of being at each time step towards the end of the episode. And the episode just means like let the agent run uh, for a number of steps. And then once it gets to a goal or you determine the time limit, then you can give it some sort of reward based on what you want the behavior to accomplish. So in this paper, the setting was simple. So you have the agent, which includes some sort of mesh. And the mesh, it just consists of vertices, and then they sort of encapture that. And then you have the environment, which is kind of a 10 by 10 by 5 space, in which the mesh can sort of move. And the mesh has certain actions that it can take. And some of these actions basically include movement of each of the vertices. So the movement would consist of up, down, left, right. Let's see if we can find the diagram. Okay, so the actions include up, down, left, right, forward, and backward. So each vertices can make a decision to pretty much move in any of these directions. And these decisions are based dependent on some other constraints. For example, they want to ensure that the mesh doesn't self intersect and that there's a sort of cohesive spatial separation between the mesh topology. So depending where the vertex is moving, they want to keep the mesh as together as possible and move in a sort of cohesive way. Now, you have the mesh and the actions and the environment. One of the most important things about RL is like, how do you encode the states and how do you encode the environment, right? And how do you have the agent observe the environment? And one of the strategies that they took here is that they create out of the environment, they voxelize the whole space. And that's a representation, let's say, of you pretty much divide the 10 by 10 by 5 volume and break it down into smaller, let's say, cubes or volumes, and they're called voxels. And essentially they represent like a unit of space. And the way that they did it is that each voxel, let's say, has some properties that represent that unit of space, and that becomes the observation. So in this case, they have a voxel state, which has the spatial states, topological states, and weighted states. And essentially what this is indicating is whether the mesh is occupying the voxel or not, and whether its topology makes sense for the actions that is taken at that observation. And that is structured in a matrix that is then fed into the algorithm, the RL algorithm, that it can process in order to determine if the state makes sense to take an action. So now, now that we have the agent, the actions, and the environment set up, then we have to create the reward functions. And they have three types of rewards that they're using to, let's say, control the behavior of the agent or constrain it. And one of them is called spatial coverage. And the idea of the spatial coverage is that they want to generate spatial coverage above a certain height, but remain a minimum amount of coverage as a foundation. So the best way to understand this is that essentially they have the mesh, and at a certain height from the bottom, they take some sort of like cross section, and then they're able to project down onto the ground what is the area cover. And from that area cover, they can calculate like how much of the space, like a sort of percentage, is being covered from above a certain height. And then they could also take a cross section at closer towards the bottom, and then calculate how much is being covered at the bottom. And that sort of provides you with a way to structure a reward function, because then you can say, okay, if you want more coverage above, then you're gonna try to like structure the reward or give it rewards so it tries to keep a higher percentage of coverage. And if you want like a smaller touching points on the bottom, then you're gonna sort of create the reward or give it reward in a positive manner so it tries to minimize the touching points, or give it negative rewards if you want to decrease like having too many points of touch on the bottom. So that's one aspect of the rewards. The second one is topological performance. And this is more or less in a way to create some sort of heuristic to test whether the mesh is supported or not, meaning like if it can hold structurally in some way. And one way they approach this, since if you were to do like a full complete FME analysis, it would be very computational expensive. They simplified it a bit more to turn, essentially, like you take one of these voxels here, and then you simplify by just checking around the neighbors and seeing if a certain amount of neighbors are underneath that voxel, and that essentially represents in a way whether the voxel above them is supported. And if it's not supported, then they give it a penalty to pretty much let it know like you need to make the mesh be as much supported as possible. So the agent eventually is going to learn that yes, it's going to maximize the support of the mesh while it creates a structure. And then finally, the other aspect of it is the site and environmental response reward, which this one is more or less based on now interacting with the environment itself. So now they introduce some sort of objects for collision. And one of the ways that you can test whether the mesh is reacting to these collision objects is that you can take the intersection of the mesh and the objects, and depending on how much it intersects, like if it's like, if it intersects a lot, then you get like some sort of percentage, and if it intersects a little, you get some sort of percentage. And then based on that percentage of collision, you structure the reward to increase kind of like not intersection. So those are three rewards that you can use to sort of modify the behavior of this agent while it's training. And then hierarchical reward is just a way to encode all the rewards simultaneously, and that just means that all the rewards are observed at the same time that the agent is interacting. So it's reacting in real time, essentially. So now if we move forward, they use the type of reinforcement algorithm that they use is a PPO, which is proximal policy optimization. So this is also model free. And then this one is useful in the way that it allows you to, as opposed to other algorithms, is pretty stable in the way that it trains. There's some sort of more mathematical parameters that he uses in order to stabilize the training, which just means kind of like how the rewards and the prediction of the next step is being handled. So the prediction of the next step is sort of being constrained in a certain manner, so it's more accurate. Um, and these are some of the hyperparameters. So these are important. And one thing to know here is like the batch size and the buffer size. So the batch size just means like how many examples you're feeding into the, let's say that the deep network. So you can't just fit, if you feed in like one example at a time, it might not do as well because it's just seeing one thing at a time. So it won't be able to generalize as well for the next step. So one of the things that they do is like you would feed 128 examples at a time. And that way it's seeing 128 things and they could be in order and but they don't have to necessarily be in order. So one of the things that these networks do in order to generalize is that they kind of collect in memory a whole bunch of examples and then they randomly sample from those samples to feed into the network to train. And if you see here, batch size is the number of examples that they're picking out of the buffer size. So the buffer size means out of the examples that they have collected over time. So the network really doesn't start, like you can do it where like the network doesn't really start seeing examples until it collects 2,480 examples in memory, or you can just do it where like as soon as it collects 128, feed it into the network. So this is important. And one of the reasons that they do this and why they randomly sample it is that it sort of, there's like an issue with creating like independently sample, what's it called? IID, independently identical, I forget what I did. So it's essentially what it's doing is like, it wants to minimize the correlation between the examples. So when you make predictions on it, it doesn't make the same prediction previously. So it's seeing a wider variety. That's kind of like the overall gist of it. So it wants to see a wide variety of examples and randomize, so it sort of generalizes better. And then finally, another hyperparameter is the learning rate, which that just means like how fast the network is stepping in the direction that it wants to optimize.
Daniel,
Yeah,
we have a question by Sujay. Like, can we
sure.
elaborate on what the hyperparameter is? One thing I
Yeah,
would
sure.
like to share is many times when like if you look at the documentation of this model,
Yeah.
they share the suggestions. So when I was reading for PPO, it was like if the batch size is more than 5,000, do 1/10 as a if the buffer size is more than 5,000, the batch size should be around 1/10. So for example, 6,000 buffer size, the batch size should be 600. But if it's less than 5,000, keep it like 1:20, or like there are some ratios which they have
Hmm.
recommended.
Yeah, yeah. But what was the question about the?
Yeah, if what are hyperparameters?
So hyperparameters. Okay, so if you have a network, let's say, you have okay. So if you have like say like a deep network, you have, let's say, like a hidden network, and then the hidden network has like hidden units, and those hidden units are called weights. And usually in literature, those are called parameters because what you're doing is like you're tweaking the weights to approximate some sort of function. Hyperparameter is kind of like controlling the overall aspect of the network. So the batch size is just kind of like a, let's say like a overarching parameter, right? The batch size is a parameter that affects just kind of how you feed the data in, so it's separate from the network. The learning rate just affects the learning rate affects how the network learns. Beta is also another function to affect how the network learns. Epsilon is it's called like the epsilon greedy function. So like if it's closer to one, what it means is that you allow the network to explore more. So the closer to one it means that you allow the network to take more random actions, right? As you bring it down, that means that the action that is taken at each time step is trying to like maximize the most reward. So it goes from, you can either set it up usually from uh, more exploration at the beginning, so it learns a wider range of the space. And then as you move through time, you can decrease the epsilon to just start taking the max action at every time step. Um,
Yeah. So it's kind of
so
controlling the learning environment.
yeah,
Yeah.
it's more or less like kind of controlling the agent to become better and better and better after kind of like exploring. So it's a very, it's kind of like very human in a way. It's like you want to like, it's like some of these principles are taken from like very real life examples, right? So you want to explore something first before you start maximizing it, right? Like if you learn any program, you're gonna go explore like any software, like you're gonna try to explore as many things at the beginning, and then eventually you get so good that then you start just maximizing like your, let's say like your
Mhm.
use of it. Um, and Lambda finally is the discount factor. And what's important about Lambda is that essentially what it does is that it allows you, so it allows the agent to discount the rewards in time, meaning that the reward that takes place further down in time is affecting the learning process less because it's too far away. So you can tweak the lambda factor to either change like you want long-term reward to affect you more, or you want immediate reward to affect you more. So if you make the long-term reward to affect you more, that means that the network essentially has to learn how to plan long-term versus like planning now. And long-term is usually, it might let you to like take longer time training because it's gonna figure out like, you know, what's the best in the longest possible time. Or and if it's immediate, then it's gonna be faster, but you might not learn as well because you're not taking like those big leaps of thinking like, you know, what's the best reward in the future.
Yeah. And like one thing I like to like just finally add, like let's say if this is your neural network, like this parameters are affecting, let's say, batch size, buffer size, the input part, and depending on the task you're training, let's say if it's related to healthcare, you might require a stronger accuracy versus creative task which you want more exploratory things. So you tweak those hyperparameters which affects the whole training part. And also like these parameters are related to, like I think like beta in loss function, there will be a term with beta where depending on the beta value input, the rate of loss is calculated, like stronger loss or weaker loss. And also
Correct.
like gradient descent, there might be like learning rate which affects like how fast the gradient should steep like.
Right. And you can also like, for example, like a lot of these parameters, you can sort of at the beginning of the training process, you can make them so they're higher up, let's say. So like there's more exploration. Maybe the learning rate is a little bit higher. Uh, and then as you go down through time, right? As you go down through the learning process, then you can begin to like anneal them or like drop them down, scale them down. So as it goes through time, it's going to become more and more and more and more efficient in the actions that it takes, and that usually helps. But after some exploration, I think what's interesting here, like when we apply it to architecture, we actually want to explore more. So
Yeah.
I would like, you know, they got like a pretty low epsilon here, so I'm not sure if they annealed it. They don't really say if like they started off with a lot of exploration and then slowly brought it down. So I'm curious. I wonder why they did that, but I would say like you probably want to anneal the epsilon if you want to explore the state space a lot.
Mhm. Cool.
Uh,
So I hope like the action space, environment, and reward are clear in like the definition.
Yeah, so I can actually show an example of a project of how you can sort of anneal these things
Mm-hmm.
and how that changes the reward function of the network. So let me, yeah, I'm just gonna share this real quick. Uh, so this is, for example, this is kind of like a plot of the rewards versus the learning rate. I mean, not the learning rate, the epsilon. So epsilon greeting. So if you can see here, like this one is over 5,000 steps. This is for like lunar lander using a dueling DQN. And you can find the lunar lander on OpenAI if you want to test that out. They have great stuff there. And the way that it works for this one, or what I was doing, is that in the first, let's say, almost close to 2,000 steps, having the epsilon be as close to 1 as possible, so like 0.999. And then after a certain number of steps, I'm just gonna like decay. And you can see kind of like at the beginning, like the score here on the right side, which it goes pretty low. It goes to like negative 300. So in this area, it's not really looking to maximize its reward. It's more or less just like exploring all the state space and seeing, you know, what are the possible actions that it can take and what it's giving you back. So it's just kind of gathering data. And then as you can see, like once I start decreasing the epsilon and the epsilon goes closer and closer to 0, you can see that off the bat, it just starts taking the best action possible. And then this just shoots up and then it starts consistently getting rewards above 200. So at this point, it's completely maximizing its actions, or it's trying to use the best action possible. So that's a good way to interpret that.
Okay, maybe like we can conclude the paper. So to summarize, I think what you would start with is like a 10 meter by like 10 by 10 by 5 unit grid. They have 108 vertices which x like can randomly move, so you instantiate those vertices, and they have 6 actions, so each vertex at a particular time can move up, down, left, right. So that covers the action space for each. And for environment, they have identified like 3 obstacles which you can define like a cube or whatever. And in the observation space, they are identifying once the mesh is uh, fluid when the agents have moved, uh, is the mesh intersecting with the obstacle, and they are discretizing the whole space into voxel. And if the voxel coincides with that, it's a negative reward. If it's not, it's positive reward. Then there is coverage reward. Ideally you want a mesh to be at a particular height so it's accessible for people, so, and but not too high, so that's why they have like from 50 to 60%, which is ideal coverage. And similarly base coverage, and then there's topological check. So that I yeah, and the rewards are as Daniel discussed earlier.
So that's pretty much like one way to approach like a problem, or how to set it up. And let's say if you want to do some architectural uh, approach, you can structure it in a reinforcement learning way. You just have to keep in mind what is the agent, what is the environment, what are the actions that the agent can take, and what are like the rewards for taking those actions in the environment. And once you have that, if you're able to figure it out for any problem that you have, you can pretty much set up any RL agent.
Do you want to briefly discuss the second paper, or yeah?
Which one was, sorry, which one was that?
Oh, I think
Should we go over that, or should we just go into the approach that we took for for putting
Yeah,
together the Unity agent.
yeah. Let's go through our Unity part. Let me maybe
You want
quickly.
to share?
Yeah, I'll share my screen. Awesome. So I think I would highly recommend, like if you're starting out, going through the docs folder in ML Agents, and like these four docs are quite were quite useful when we were starting out. And one thing is, I'll show you the key things. Okay, where is the example document? Yeah. So this was a starter point for us where we first implemented. So the way this project work is, you have a sphere, and that's an agent. It can move around, it can rotate, it has velocity, and the task is the sphere. Once you start pushing the force in x and z direction, it can fall off this plane. And the goal is that the sphere should hit the target cube instead of doing a random action and falling off the plane. So the way they have implemented is, uh, first create a flow plane and the target cube. We need that flow plane because of the rigid sphere, sphere and rigid body mechanics we want to use later. And then they created the game object of sphere and give a position. They grouped it, and here is where the main uh, agent definition happens in the C sharp script, where you there's also a quick installation. So in Unity, uh, from the package manager, you need to install ML agents, and then once it's installed, you can call those Unity ML agents package in the C sharp script. So once that is done, the biggest thing which one needs to understand is like this three aspect. On episode begin, observation space, which is done through this sensor, and action space through action buffers. I think this is the crux of whole RLN.
So I was gonna say, so if you take a look at those, let's say three functions, and we relate it back to what we just discussed in the paper, like on episode begins just means like, on each episode. So like when you're gonna start training the agent. So every time you want to start training the agent, right? And then collect observations, it's pretty much like, what information are you receiving from like the current state? So that's where you're gonna encode like your state, and then a state of the environment, and then on action receive. So what actions are you gonna take, and right, like what out of all the actions that you can select, what actions can you take there?
Correct. And from here onwards, like whatever agent you define, you need to initialize, like instantiate uh, at start point. It should start at this low position and set the velocity to 0. And the way it works is, for each next step, you define an action of putting the force to the sphere in x or z direction. And once you apply the force, it will gain velocity and it start moving. So initially it's 0. And one good thing is, while training, you want to randomize the location of the target, so it's not like learning a particular specific behavior. So that's why for each episode begin, we are randomizing the target position. So once that is done, this is like uh, basic environment initialization. And now the next step is observation in those environment. So depending on the problem you're solving, one might need to rethink what are some parameters which affects the solution. So if I want to climb a hill, like I would like to know the elevation or the target point. So those parameters or features should be on my observation space. So here in the observation space, since we need to reach the target, we need target locations. We need to know the current position of a sphere. So that's why this dot local position, and also velocity in x and y, because depending on the action you take, uh, there would be velocity in x and y. Maybe when you're near sphere, you want slower or faster. So the in the learning observation space, each action affects this parameter. So those parameters should be observed. And lastly, the action space is just pushing the sphere in x or z direction. So we identify those and then we add force to that sphere. And like we need to terminate the episode if the sphere falls off the plane, or if the sphere reaches the target. So that's what is encoded here, that if distance less than 1.2 float value, set the reward that reach the target and end the episode. If it fall, just end the episode. You can also have negative reward here, that it falls off, penalize that behavior. And yeah, so this is compilation of what we discussed: action space, end episode, and yeah, this is like just assigning the agent class to the target, and you can also test it through your keyboard. So, so I think we should briefly go through this setup, right?
Mhm.
So there are two key aspects to this setup. Is one is installation of ML agents library in Unity. So here is our Unity. Here is our virtual environment. So the way it works is we install all the packages like ML agents, PyTorch in virtual environment. Then start a YAML file which contains the PPO policy with all the hyperparameters. So we'll say ML agents learn PPO YAML file for 3D ball, and then it starts the environment, and then it calls the Unity to get all the environment, observation, action space from Unity with all the changes we made in that environment. Once it calls back, it reads the parameter and then starts the PPO training here. And at the end of this, whatever hyperparameters you decide that, okay, run for 2000 episodes, it will do the training, and then it will generate a train model, which you can then drag and drop in Unity. And in future, you can run inference directly based on the train model. So this is the basic environment setup which you are supposed to do. And it didn't, it took a bit to install. So uh, yeah, anything else, Daniel, we should discuss before we go through our code?
I don't. Do you want to kind of? Should we show like how to install like the environment in Unity? Like if you go to Unity and then you have to like if you have an Anaconda, you're gonna have to. I don't know if you want to show that, like how to create like the environment and how to like do like pip ML agents. Uh,
Yeah, so I can quickly show, like in Windows. Like first you
Yeah.
click on show preview packages, and whatever release, I think this is important to mention.
Yeah.
So
Just like the struggles that we had to trying to figure this out.
so how it works is you select a release version. So like we went for release 15, then you download the code from here, and it will like be a zip file. And when you are installing the ML agents, match to that release. So we use March 17 release for those, and even March 17 for this. So now, uh, so the way I get it, this ML agents lib package in Unity is basically a reader. Like
Mhm.
all the trained models, it can infer in packages, and like in C sharp script, defining action space, environment space, action buffer, on episode load. So all those library functions is being accessed through this. The virtual environment creation is just for training purposes. So this package can't train. So the let me see if I still have the history in my virtual environment. Oh man. Uh,
Oh yeah, right. Right.
yeah. So yeah. So first step is conda create like the name of the environment in the Python version. Once you create that, come on. Yeah. And then I think pip install. Wait, how do I find? Yeah, I think I install like PyTorch. Like, okay, once you create the environment, activate the environment of ML agent. Then the folder which you downloaded from GitHub, you need to like change the directory to that folder. So this is the one. And then you install PyTorch, like with this link. And after that, you install ML agents, and yeah, that's it.
That's all you have to do.
I think they recommended this. I haven't seen like usage of this pyzq.
Yeah.
So now everything is installed, and you if you want to check whether it's installed right correctly or not, you can just type ML agents learn, and it will show like the version and details of that. So that's it for let me see if I have, yeah. So this is the zip folder which you get from GitHub, and all the templates if you want to start working and upload directly to Unity, you can find in project, assets, ML agents, and examples. So we looked uh, grid world and all other examples directly. So if you just like import this example in Unity, you have the environment running with all the scripts scene to start with. So this is one important folder you would use frequently, and another is this config folder. So remember we discussed about PPO and SAC. So basically you would select based on the environment, you can create your own YAML file or select the one which, if you're working with the basic example, and you will call that example in the virtual environment. So like ML agents learn dot slash config ppo 3D ball YAML, and then run ID is like basically you create whatever ID you want for training. And once you do that, uh, it will start calling, listening to the port, and press the play button in Unity. And then you just need to press the play button and it will start training. So that's how it looks easy, but you sometimes you got to debug. And what the next step uh, you can do is you can visualize the results in TensorBoard. And so I created another virtual environment and basically ran TensorBoard log results. So the way it works is once you start training, all of your results are saved in results folder, uh, and in TensorFlow you can visualize like what's the reward, how much training is it improving, or so. Yeah, so should we, let's see, hopefully I can do a demo right now.
Yeah, that's
So we
yeah.
all like we worked in Daniel's PC. I just did a quick I uh, I I made a new project in Unity and use your the script we worked on yesterday.
Mhm.
Okay, okay, it's create object, which is our YAML file, and flying mesh 4 4. So now we have called in the virtual environment for Unity to instantiate the PPO and hyperparameter. All right, so it's waiting for Unity, and now all we did in this is created this create object file, which has like the mesh size, action space, which will go in detail soon. But let me show how it works. Come on.
You gotta watch out for the cameras because it just flies.
I tested it in the morning. It was working.
Yeah.
Trust me.
Okay. Awesome.
Let me see if. Okay, it's reading. Okay, it's working.
Oh yeah.
So it once you start, it will like detect the hyperparameter. Okay. So right now, like there are 16 vertices which are moving randomly, and we have reward function that if it the crosses beyond a particular boundary, it will terminate. So the things which we need to work on is improving the reward function, and also like end episode termination. But like spending like from 10 a.m. to 3 a.m. working on this, even this flying mesh was satisfactory.
Yeah.
Okay.
It's learning something.
it's,
It's learning
it's
to fly.
okay. Let's maybe go a bit deeper into create agent. So yeah, Daniel, take over.
Okay. So the first thing in so now that you have the Unity environment open, then I don't know, Mary, do you want to show like how to create like a script? So like it brings you into like the Visual Studio. So you have to have Visual Studio. Um, and then you do create a script, and then if you double click on that script, that should take you into like Visual Studio code. Um, and then it provides you with this sort of basic template, which is you can modify this and you can change it to like whatever you want, like agent. But the important part is like you have the void start, and then you have void update. The void start is kind of where you would place like your, let's say like your functions where you would want like when you run the script in Unity where you want things to start happening, let's say like the functions start working. Void update, it's that's more if you want to see a move in Unity. So like when you hit the press play button in Unity, what happens is like it begins to move like some sort of iterator per frame. So void update just I guess make sure that as it's playing, it's gonna update something. So you can kind of, it works kind of like if you think of like as a for loop, it just keeps going and going indefinitely. And so you can add something here that you want to see move. But for our case, we're gonna take that out because we don't want to see that. Um, So now if you go to, a create object. So now the first thing that we kind of did was we had to figure out how to create some sort of mesh object. And for the mesh object, you need, so we have the public class create object and then the agent. And then we have the required component type of, which is a mesh filter. That just means like to select a mesh. And if you go, if you go to Unity, like how do you create an object? So the way that I did it, if you right click there, you go to create empty, and then you add a component, and then you go to mesh filter and add that, and then mesh render. And then the mesh render is just to give, change the materiality or the color. So you can change like the elements material up top, and there's some other properties. Okay, so once you have that, then and you have the script, so now you can sort of begin to create the mesh. And one thing that you have to think about is like how big do you want to size, how many vertices or panels do you want to have in the mesh. So that's where public int x size and z size comes in. And then you have the way to, so over there in void star, you have the mesh, you create a new mesh, and then you're filtering out the mesh from the get component mesh filter. And then you have two functions, one which is create shape, and then the other one is update mesh. So the create shape function, what it's doing is pretty much taking the parameters that we indicated above for like the size, and then storing that into a vertices array, and then running a nested loop to create those vertices. And what it's doing is just generating like the XYZ coordinates for each vertices. And then once you have that, if you want to visualize the mesh, you have to create like the triangles. And one way to approach that is to, if you think about it, you have to run through each of the vertices and group them together by indices. And the way that Unity works is that you have to order them clockwise. So you have to think about how like you would structure that. And here's like one way to do it. So this little script here just generates your triangles for the mesh. And then if you go down here, void update mesh. So this is what creates the mesh in Unity. So you have mesh.vertices equals the vertices that we created above, and mesh.triangles is just the indices of the vertices and how they're supposed to be grouped together. And then you feed that, and then you do mesh recalculate normals to make sure that all the faces, all the mesh faces are facing the correct direction, so you can visualize them in Unity. The next part, so the first part was just creating the object. The second part is now running like the setup to create the reinforcement learning algorithm. So we have on episode begin, and pretty much what we're doing on each episode is we're creating like a brand new mesh. So it's like a clean flat mesh. And then as you go down, you run in the collect observations part, which is essentially what we're doing is for each vertices. So the meshes in essence acts like as a one agent, and the vertices are just kind of like parts of that one agent. So we're adding observations for each of the vertices here. So that's what we're for looping through all the vertices and adding an observation for each vertices. And what is being recorded here is just the positions of the vertices.
Yeah, and like just to give some context, so we are using like total 16 vertices. So the observations are 48.
Correct. And then here now we're creating like the actions. So these are the actions that we are allowing each vertices to move. And the way that you have to do it here is that you have to essentially create kind of like an index of the functions. So in this case, we have a total of 7 functions. So no action means like don't move, up, down, left, right, front, and back. And each one has a number associated with it, which is going to be used as input for the array that Unity uses to index out the actions. So if you scroll down, I guess, yeah, on action receive, you create this function, action buffers, and then uh, so one way to do this is that since we have actions for each of the vertices, the way that it works means that each vertices has a total of 7 actions that it can choose from. Um, and the way that the Unity environment allows you to do it is like you can create like a branch, and we'll show that later how that works.
Yeah,
Um,
I think like just for clarification purposes, we can show an example where uh, it's a bit more simpler.
yeah.
Sets ML agents. Which one should we go, like 3D ball or grid world?
Uh, the 3D ball was kind of very simple, so
Okay.
I guess that one might be.
So
So
like
this one,
here, yeah, observation is pretty straightforward. I think. Wait, where is? Yeah, here it is. So they are using continuous actions, and we are using dot discrete actions.
mm-hmm.
So basically, imagine this like 0, 1, like as different independent actions. Like this 0 is, let's say, I wanna jump is 0. Uh, I wanna call someone is 1. So like totally independent action, and each this action can be discrete or continuous. If it's continuous, it can output value from -1 to 1. If it's discrete, in Unity, you need to define how many integers, like how many discrete actions. So if it's, let's say, uh, discrete action 1 to 4, so the output of this would be any number between like 1 to 4. So the way you work that in Unity is in game object. Uh, we made this like if it's just one uh, action, you define. Should I change it? No.
Yeah, so you would have to add behavior, yeah, parameters.
So in behavior, you just say okay, one branch, or I
So
can
if
just say
you,
yeah.
yeah, if you're doing behavior for one agent, let's say, then you only have to specify uh, kind of like it would be like one branch, right? Because it's just for one
Mhm.
agent.
Yeah.
Um, and then you can assign it for that one branch the number of actions that you want that agent to have.
For some reason, it's not changing. Yeah.
Oh,
So yeah.
maybe it has. Well, you can show it off with the other game object that we created. So here, if you, for example, like we said, so this is kind of like the other aspect. So we have here vector observation, right? And that's the space size, and it's 48. And in our case, it's 48 because we have 16 vertices, and each vertices has 3 coordinates, right? So if when you multiply that out, you get 48. And then we have the actions. So the discrete branches, we think about them as like the number of vertices, right? And then the branch size just means how many actions each vertex could take. So in our case, it's 7, and that's why you see like all the sevens down the line.
Yeah, and it's not necessary that you have like same action for each branch. So let's
Mm-hmm.
say in first action, let's say I want to it's action about jumping. So no jumping, jumping high, jumping low. it can be three discrete action. And then another is calling. So no calling, calling now, like it can be a two discrete action. So depending, like you can create like custom branch size based on the action you take. And one important fact is you need to change the environment like based on the action. So that's why like we created those 16 branches here, where the whole training part is at each time step the model will say vertex 1 should move in either up or right, vertex 3 should move left or down, like each action for each vertices. And that's what we are training for.
Mm-hmm.
And here it shows, okay, once we define what are the branches, we need to say, okay, the branch, since we have like 7 actions, it will predict any value between 0 to 6. And once that value is done, we say switch that value and then change the vertices to like up, down, left, right. This is
Yeah,
just a test run.
yeah. So, but this one, it's like it's looping through all of the vertices, and at the same time, it's looping to all the branches, which should match the number of vertices. And then each branch is gonna output like the action variable, and then we check in whatever that action variable based on what we define above as like the index for the action. And then as it goes down, check in like the cases for the action, then that's gonna cause some transformation in the vertices, and then the mesh gets re-updated after it runs through this every time.
Correct. So let's say if we have like this 9 vertices, we assign branch to each vertices, and that branch like not that discrete action will predict any of this 7 values at a time.
Mm-hmm.
And we need to like move these vertices, so that's why we had that another for loop where go through all the vertices, check what uh, action it has taken, and then update that vertices based on that action. I think that was the one which took a while to debug, but yeah. And then rest is update mesh based on new vertices based on the action we took.
Correct. And then like if you take a look at like how we set the rewards, um, like we made it very simple because we were just trying to get something to work. But what the rewards does here, and like obviously you can set your own type of rewards, and but we're sort of looping now through all the vertices again, and we're checking whether it goes past 50 units. And then if it does that, then we give it a negative reward and end the episode. And if it and we do that if it goes if the X, Y, Z go anywhere past that, then we give it a negative reward and end the episode. So we haven't assigned any positive rewards. We're just kind of like teaching it to like stay within like some sort of boundary.
Mhm. And lastly, I think many times in one of the past project, like like we worked on a project and defined the environment, but it's before training or after training, it's difficult to understand whether it's working properly or not, whether the agent actions are being properly defined. So
Mm-hmm.
one way to check out is like through heuristic, where all the action space you defined, you can do assign a keyboard function like keyboard key. And in Unity you can play, okay, keyboard left, do right, keyboard uh, any D, move Z. So that's why before training you can do a test run whether these functions are defined properly and working by typing this like assigning a keyboard key to it. And the way you do it in Unity is uh, in behavior type you just change it to heuristic only, and do like a testing on your keyboard how the agent is moving in action space, and then while training you again change to default, and then once it's trained you can keep inference only or leave it to default. Yeah, and I think uh, once you do that, you you added the mesh uh, renderer. You also need to add a decision requester, and yeah, I think that's it, and we are also running good on time.
Yeah,
uh,
so that's pretty much it.
all right, let me check. If you have any questions or things you want to clarify, let us know. Okay. I think, yeah, thanks, Sujay. Uh, this is like when this might will open a lot of opportunities for like human machine co-architectural programming or structural behavior. Like it's it, uh, uh, we are happy that we got the basic environment running, so now we can add more complexity at top of it.
Yeah, definitely. I mean, because we can also like we got the basics, and the idea we were trying to do is to sort of replicate something similar to what the paper was doing, and maybe add some collisions, and then see how we can, I guess, structure the mesh so it doesn't self-intersect, right? And like the most important part is like when you think about like how do you create like your own agents and like your own environment, there's like a lot of process that goes into like thinking just how to make it actually work the way you envision it. So that's kind of like an important part of all that. um,
Yeah, even like the the one of the thing we would like to share is the discrete action branch was a good concept we grasp along the way, because earlier we were not sure whether we should make like all the vertices as multi agents and how to work around that situation. So
yeah,
uh,
I think that helps a lot, right? Or be able to structure like that, because then if you think about it, it's kind of like, oh, so that's the other thing, right? Like how do you structure your agents, right? Or agent, do you want it to have multiple parts that extend out of it, and then it's you have a kind of like an overall brain, and then that brain is making decisions for all its parts, right? Or do you want to have something where you can get more complexity, where you have multiple agents, and maybe those multiple agents are working towards like one goal or something like that. So you can get like really interesting things, I guess, once you start playing a little bit around that.
yeah, I think like uh, the blog, I think there was one documentation you found which was quite interesting. Do you have the link where like we were reading about the discrete space?
Yeah, let me see if I can find it.
And I think there are a lot of things you can work with ML agents. Is I think they have added more on curricular learning and also this discrete action masker. So in discrete, like the actions, you can also avoid that few actions for the agent, and you can code that. So this is another thing where maybe you can have a boundary or a pit and totally avoid that action. So
Oh yeah, so I have.
you have
Yeah,
that.
I'll
Okay.
yeah, I'll share the link. All right.
Right.
So this it's in the scripting API, right? Uh, and this talks about like how do you structure the actions. And this took us like a little bit of time to figure out yesterday, because we were trying, like Mayor said, like we were trying to figure out whether we have multiple agents or we just have one agent that each of his like body parts would have its own actions. Um, and then in this API, it talks about, so this is the function that you would run that under, like action receive. And then what it does is like that there is a vector action, and that's kind of essentially the number of the actions that the agent can take. Um, so your implementation must use the array to direct the agent's behavior for the current time step. So at every time step, it's going to choose like a different action. In our case, it was like 16 actions that it was choosing at every time step. You decide how many elements you need in the array to control your agent and what each element means. Um, and then you can implement a heuristic. Okay, so that was what you talked about. And then actions for an agent can be either discrete or continuous, depending on which type of actions space the agent uses. So like the important part is like, what's the difference between like discrete and continuous? Continuous is something that you don't have, like, let's say like the environment is not broken into like some sort of grid, right? It's kind of like it's always moving. Maybe you have, instead of like a step, like instead of saying like move left, move up, you're gonna say like move in this direction at this velocity, and it could keep moving, like it could just keep going. Um, and then you can claim the values for like those continuous functions between -1 and 1. And so this is an example of like when it uses a discrete space. So do nothing and then move one space into each of these directions. So the agent picks one of the actions, and then here where it says you can define multiple sets or branches of discrete actions to allow the agent to perform simultaneous independent actions. For example, you can use one branch for movement and another branch for throwing a ball left, right, up, or down to allow the agent to do both in the same time step. So that's what you were saying, man, right?
Yeah, that is quite important. Like that paragraph solved a lot of things for us.
Yeah, which is kind of interesting because, like, if you think about it, like, we can have, like, let's say in our example, like the mesh, like, we can assign some vertices to just move in certain directions. They don't know necessarily have to have the same number. So maybe like the edges only move like up or down, right?
Mhm.
And then everything else in between can move in other types of directions. So you can play around with that type of stuff and see what you can, I guess, what the rewards would lead you to think actions. Um, oh yeah, and this is the important part. So the action vector of a discrete action contains one element for each branch. The value of each element is the integer representing the chosen action for that branch. The agent always chooses one action for each branch. So that was like what helped us solve the problem. Once we got this, like we were able to like make it do things.
Yeah, and it was like very late in the night.
Yeah.
Cool.
Um,
So I think maybe we can conclude. Sujay has a question that do we have to train TF model via ML agents, kinda, or we can already import. Let me share my screen real quick. So you can use a pre-trained model. So if you look at any like the examples which they have in project assets, ML agents, let's say crawler. So they already in the preset examples have TF models shared, and you don't need to train. You can just drag and drop in the Unity environment and start using those trained model. And basically, you can. I have seen OpenAI Gym compatibility with Unity. The way ML agents is helping is it's like this TF model. I think they like are in Python compatible language environment, and Unity is on C sharp. So we need like a wrapper and a training ecosystem which converts from like Python to C sharp or eases the workflow from C sharp scripting game objects interaction with the reinforcement learning part. So that's where I think ML agents help. You can totally do like a training on Colab and then do some conversion and import it in Unity. Uh, it's it's just the workflow as we saw. You just run the virtual environment and press play button and Unity, and all the custom action environment can be easily integrated. So that makes it very useful.
Yeah, I think what's cool about Unity is that it allows you to see what's going on, right? Like if
Yeah,
you're using like 3D stuff, which I guess we like as architects, you can like kind of see it in action, and that's always fun. Oh, Mary, the other part was like you can parallel train, right? But we weren't able to get into that. But that's another cool part.
yeah. Like in the example, you will see like a ball training of 15 different balls trained parallelly. And also, I was reading about it. You can also create parallel instances of Unity itself and
Mm,
in the training. So a lot of possibilities.
yeah, definitely. Yes, awesome.
Cool. I think we reached like almost 1.5 hour mark, and it was an amazing session. I really enjoyed. Thanks a lot, Daniel and
Yeah, thank
Sujay,
you.
for attending.
Yeah, that was fun.
Good. So next week, it's I'm in talk, but mostly it's on generative algorithms. So I'll keep you posted on the content for it. Cool.
Awesome.
Have a nice rest of your day and night.